Okay, so in this video we're going to take a look at an example related to the DC machine, and it's a fairly straightforward example, but it'll set the stage for a second example, and in that one we'll use certain elements of this example to further develop our understanding of the way DC machines work. But essentially we're given here a set of test conditions, I guess, if you will, and so it says the following table gives the open circuit armature terminal voltage of a separately excited DC machine spun externally at a speed of 1500 RPM as a function of the field current. So you have this, your armature voltage, this is your armature voltage, and you have it as a function of the field current. And then it asks you to calculate Kf for the linear region of the magnetization curve, meaning we'll have to somehow determine what the magnetization curve of this set of parameters sort of produces. And then it says to calculate the machine of the speed when it's operated as a motor with some certain conditions. So the first thing we have to ask ourselves is, how do we determine the magnetization curve? Why don't we approach that part first? So the first thing we do is we say that since this is open circuit, so let's start with part A. So this is open circuit. And what does open circuit imply? Open circuit implies that IA is equal to 0, which is very important. Now if IA is equal to 0, that means that VA equals IA RA plus K phi omega M, which is our equation for the DC machine. We'll simplify, this will go to 0, and that means VA is going to be approximately equal to E, and of course we know that this thing here is E, which is K phi omega M. And so if VA is equal to E, this is K phi omega M, means we can determine what K phi is using omega M, and omega M is given to us in the question. So what we're going to do here then is we're going to rearrange this, and we're going to say then that K phi is equal to VA over omega M. But you'll notice the question gave us RPM speed, and this is omega M, this is angular velocity. So what you have to do is, you have to first take omega M and convert that, so that 1500, you divide by 9.55 to convert it into an RPM, and that gives you 157.1 radians per second. Now, what we're going to do is we're going to take this 157.1 radians per second, and we're going to take all of these values of VA, and we're going to divide them by this value 157.1, and that'll give us K phi for each of these cases. Then we can plot the K phi versus IF curve, and then we'll get the magnetization curve. And so rather than sit here and calculate each one individually, I've done it beforehand, so it'll be convenient for us for the sake of this video. And so these are the numbers you should get when calculating the values of K phi. Now, it asks for Kf in the question, though. It doesn't ask for K phi. Now, if you recall, Kf is the sort of slope or the linear approximation of the magnetization curve. And if you look at these parameters, you'll notice that between 0.5 and 2 is a linear sort of region, I guess. So the data seems to suggest that 0.5 amps to 2 amps is the linear region, meaning we can say K phi is equal to Kf IF, and we can determine what Kf is. It's kind of a slope, I guess, so by the change in K phi over the change in IF over these regions. And you'll get, if you solve these numbers, I mean, you'll get, so let's say 0.738 minus 0.197 divided by 2 minus 0.5, and you'll get that Kf is equal to 0.394, and the units are of inductive quantity, I guess, or characteristic, or nature, let's say. Now the second part, which is fairly simple, gives us a set of conditions, and it asks us to find what the speed is under those conditions. So part B, and I guess all this is part A. Part B says that, says what? It says IF, so IF is 2.5, K phi is 0.89, and based on these two conditions, well, the question doesn't say this, the table says this, so I guess we should take a step back and not get carried away. So IF is 2.5. Then we go to our table and we say when IF is 2.5, K phi is 0.89. If k phi is then 0.89, then what we can do is we can use the fact that k phi is 0.89, and we can say that Tm is k phi Ia. And you can determine what the value of Ia is in this case, and this will be 45, which is given to us in the question, which is Tm, divided by 0.89, and that gives you 50.6 amps. So that's your armature current. Now, using your armature current, as well as the other parameters of the machine, you can determine the speed of the machine. So this is VA is going to equal IA RA plus K phi omega m. And you can rearrange this expression for omega m. And if you solve it using all the parameters we've been given in this, so let's say 145 equals 0.22 times 50.6 plus 0.89 omega m. And again, these are all the parameters we have in this question. You'll find that the speed is, so omega m is 150.6 radians per second. And if you want to convert that to a revolutions per minute or an RPM, what you'll get is 1438 RPM. And this makes sense because it tells you that it's spun externally with 1500, and that's the open circuit conditions sort of here. And then it shows you that in the event that there is some load, let's say, or there is some torque applied, then this speed is lower, which is what we expect. So, recap of everything that we just did. We had this table, and given this table, we were asked to determine Kf. To determine Kf, we would know where the linear region exists. The linear region depends on k phi. So we found k phi using this expression here, and we solved k phi for all of these. Now, if you looked at all of these numbers and you looked at where the constant the constant increase is, which is the linear region, a constant increase implies linear. So you would see that this is the linear region, and I'm sure you can probably extend it for a couple of entries as well, but it's fairly linear for this part. And based on that, you can determine the slope of that region, which is what we defined Kf as in a previous video. And then you can determine, based on that, well, I guess that's independent of this part. In any case, then you can determine what the conditions are for this speed of the machine, I guess, when it's operated as a motor, using the fact that IF equals 2.5 gives you a K phi of 0.89. And then you can plug that into your equations. You can determine what the current is under that condition, and then you can determine the speed here. So I hope this was helpful. If you have any questions, feel free to leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.